Hi, I'm Adi, and I'm here to present our work on improved training of convolutional filters. We are all aware that CNNs have been widely successful, but this success has come at a cost of overparameterization and added complexity, which means slower inference, and it needs a lot of data to train. And because of this, there has been a lot of surgence in network pruning and model compression-related works. And when you look at the results of pruning, what this shows us that it is easier to take a larger network and prune it to be a smaller size than to train the same size network from scratch. Here you can see the black triangle versus trained from scratch. So we looked into the filter importance of these ConvNets, and we found that a lot of these filters, they hardly contributed towards the performance of this network. Now, this kind of graph, it is expected for networks like VGG, which has millions of parameters, but we were surprised that similar kind of graph occurs even for a shallow, tiny ConvNets. Therefore, the question we wanted to ask is that, are these two problems related? That is, inability to train a small network from scratch, and the fact that even in a small network, a lot of the filters hardly contribute towards the performance of the task, even though they are already underfitting. And this is motivated from a lot of results from pruning, which shows most models can be pruned, and from the recent hypothesis which says that it is easier to train deeper networks because it has ensemble of a lot of subnetworks, and you just need one good subnetwork to do the task. Therefore, our first key insight was to train a network such that its filter importance is more uniform, and while training, we will prune and reinitialize the filters in order to explore large number of subnetworks. So when you look at the RePr training process, it looks like this. First, we initialize a network and train for a certain number of iterations, and then we measure the filter importance. That is, with some criteria. I'll talk about it later. And then we prune the network, and for some iterations, we train only this subnetwork, and then we reinitialize the prune networks. And here you can see at point A, some % of the filters were pruned, and at point B, these filters were reintroduced, and with a new set of weights, not the same old weights. And you can see this has a lower training accuracy compared to the standard training, which is in the orange line. But however, we are more interested in the generalization, that is the test accuracy. And when you see the test accuracy, when these prune filters are reintroduced, that is at point D, you find that they find new features which are more useful, and they have a better generalization. And you can repeat this process with diminishing marginal returns for several times. And so at this point, the problem is how should we rank these filters in order to do this process? And when we looked at the filters, we found there was a lot of correlation between the filters of the same layer in the ConvNet. And here you can see the layer 2 has a lot of correlation. So our second key insight is to minimize these filter correlations. That is, we find the orthogonal projection of all the filters in a given layer, and then we sum the rows, of course without the diagonal, and then that gives us how much each filter in that layer overlaps with other filters. And we find that this ranking has a very good correlation with the Oracle ranking if you had access to such. And it performs as well as the Oracle, even without needing a lot of computation that Oracle would need. Therefore, the final solution we propose is to train it with a RePr training scheme, and then to use the interfilter orthogonality ranking. And here you can see on the right, the correlations of the filters when done with this kind of training significantly reduces, especially in the later layers. And here we saw the difference in the result of RePr and the standard over various other ranking schemes. And we can see that the combination of RePr and ortho leads to the best results. And we have more results in our poster if you're interested. And while this technique might be similar to dropout, this process works regardless of whether or not your network has a dropout, which doesn't generally work so well for ConvNets. And our technique compares favorably with dense sparse dense and BAN, which are similar techniques. Although this was designed for shallow ConvNets, we found that it leads to small improvements even in a deeper nets like ResNet 100 and ResNet 152. So in summary, we want to minimize the inefficiencies of filters by reducing the correlation, and we want to allow the model to explore large number of networks by doing this RePr training scheme. So please come to our poster number 7, and we can talk more. Thank you.